A 400-pound engine is suspended from the ceiling by two chains at 60 degrees from the ceiling. How strong should each chain be to withstand the weight of the engine? So here we have a diagram so we can see what's going on, and they make this angle of 60 degrees with the ceiling. Now, because we have parallel lines drawn here and this transversal alternating interior angles are equal, so this angle is 60 degrees as well. Now we could use a right triangle then if we call this vector, it's a force vector, and we'll call it F1 for force 1, and the magnitude of that is the length of that vector. So we could use trig and connect that with, we want to try and find our x component of the vector here, and so we could use here cosine of 60 is adjacent over hypotenuse. That's going to be adjacent over hypotenuse, and we could solve that for x, and what we have is the component of the force that's acting in the x direction. Now we could do the same thing to find y, and this time it's going to be sine, so we'd have y equals the magnitude of F1 multiplied by the sine of 60 degrees, because we know that's adjacent over hypotenuse. So we could express our force vector as the x component and the y component here, and here is our first vector. Now we can similarly do the same thing over here. For this vector, we'll call it force 2, and we've got our x and our y, and we're going to get the same kinds of components because we essentially have a 60-degree angle right here as well. But the only thing different, because we're in quadrant 2, x values are going to be negative. So we can express our force 2 vector, but we need a negative on the x value, and then our y value is the same. Now, these two vectors, if we took vector 1, force 1 plus force 2, we need that to equal or be able to withstand the vector that has to do with the weight of the engine. So this is weight here is a force, and so we know that and that's all acting down here. We could call that force 3, and we would want those to be equal so that the chains could withstand that force pulling the engine down. Now that's all expressed in the y direction, everything going down, so we could express that as 0 for our x component and negative because we're going down 400. Now we could take these then and put in the pieces that we know and be able to solve this for F1 and F2. So we are going to look at the x components, and we'll take the x component of force 1, and so that would be magnitude of force 1, and the cosine of 60 degrees is 1/2, and then we will add to that the x component for force 2, so that's minus magnitude of F2, and that's also going to be multiplied by 1/2, and we want that to equal the x component of the engine pulling down, so that's 0. So we could cancel these out, and basically this tells us that the magnitude of the forces are equal, and we could kind of see that as we saw the symmetry of the diagram here. So now we're going to equate y components, and so we have, for the y component of this first vector, we have magnitude of force 1, and then multiplied by the sine of 60, that's square root 3 over 2, plus same thing here, so we could actually just multiply that by 2, and then we would want that to equal 400. So we can now solve for the magnitude of F1, and that's going to be 400 over square root of 3, and we could punch buttons to get an approximate. That's about 231. So what that means is each of these chains needs to be able to withstand 231 pounds to be able to hold the weight of this 400-pound engine.